Okay, so next up we have Ghada. She's the security research engineer at Orange from France, and she will talk a little bit about attestation for mobile networks. So please.
Thank you, Mohammed, for the invitation and the introduction. So as my presentation is going to be about attestation in and for mobile network, I would like to start by recalling what is a mobile network and what is the architecture of the mobile network, especially the last generation. So regardless of the generations, a mobile network is composed of three parts. We have the end user equipments. In 5G, you call this 5G devices. Then we have the radio access technologies that are connected to the core network that will host user plane and control plane network functions. So the charging, the authentication, the routing, and so on. And a mobile network should be able to provide some services to verticals and has also a connection with external, private, and public IP networks. So now, if we zoom on the 5G core network, you may know that in 5G, the keystone is virtualization. So the network function have not anymore dedicated hardware, but they share the available infrastructure, hardware infrastructure. That's why we have a layered architecture where on the bottom we have the hardware resources, then you have a virtualization layer, and on top of all this, we have the virtualized network functions. And all the layers are being managed by the operator, who is going, for example, to set up slices for the verticals. So the operator is going to use some VNFs, virtualized network functions, that are provided from one or multiple providers, and that are going to run over hardware that is also provided by one or multiple providers. So the question now is, in this scheme and this view, it looks like the operator is managing everything. So the question is, why do we need attestation in this context if the operator is managing everything, is controlling everything? Actually, with the arrival of new actors like the VNF providers, the hardware providers, the question is, who is responsible of what? Who can I trust? We are not anymore in the trust model with two parties, where we have the end user at a side and the operator on another side. So we have a lot of actors that are involved in the mobile network. So the operator needs measurable trust and measurable security in order to verify his own network, but also to achieve his commitments with regards to the vertical that are using its network. And inside EU, many organizations are talking also about sovereignty. Where is my data in rest, in transit? Who is treating it? Who is using it? And we go back to trying to prove a property about something, either it is data or it is an equipment. For example, at ELISA, they proposed a certification scheme for products. And now they're discussing and trying to propose a certification scheme for infrastructure, but in a different way, in a new way. When we certify a product, usually it's one shot before putting it on operational context. But in infrastructure like 5G, which is evolving all the time, we are not using the same VNFs, not the same hardware every day. So what we would like to have is certification infrastructure, but in a dynamic, in a continuous way. And again, in the same spirit, some guidelines, European guidelines like NISA2, CRAA, they also mentioned the need of proving some properties. That's why today, as an operator, we are really interested on this kind of approaches, attestation protocols. So this leads us to say, what is really attestation? So in a very simplified view, because the previous speakers have already presented this, so it's a simple protocol, challenge response protocol, where we have at one side a verifier and then another side prover. The verifier and the prover could be different entities. So the prover could be a network node, it could be a group of network nodes, it could be nodes from different types, from the same type. And regarding the verifier, it could be a third-party attestation server, could be the vertical, could be the operator. So it depends on the context and the use case. And I would like to stress here something that I used the terminology verifier prover, but I know that there are some differences between standardization organization like in ETSI, they use attestation server and attestation agent. In IETF, I think they use verifier attester. So, but it's in the same spirit, but it is different terminology. Another point that I would like to mention is that when we talk about attestation today, it's like we assume that it is verifying the state, the integrity of the prover, of the target. But actually, attestation is larger than that. Attestation could be about any property. It could be, for example, key attestation, proving that a key has been generated and stored in a given area. It could be geolocation, could be proof of transit, could be a combination of protocols. But I know that usually when we say attestation without precising what is the property, it's integrity. In my presentation today, even if attestation is large protocols, I'm going to focus on integrity and more precisely on a family of attestation protocols, which is called deep attestation. So deep attestation enables to verify the integrity of the VM and the hypervisor, so all the virtualized infrastructure. But in addition to the verification of the integrity of the infrastructure, there is a new property that is offered by this type of attestations, which is layer binding. This means that the verifier is able to check that the orange VM is really running on top of the white hypervisor. And I would like to anticipate some questions. Why did we consider this work in my work? Why did we consider this architecture? So VM with hypervisor, 3 layers. Why didn't we consider other type of execution environment? Also in our work, we consider TPM and VTPM as virtual root of trust and hardware root of trust. Why did we use all of this in our work? Actually, the answer is very simple and very easy, because the first time when we discovered the deep attestation protocols, it was by reading some ETSI specification, and ETSI used this kind of architecture at the beginning when they proposed and described the deep attestation protocols. So let's now look to what ETSI proposed to solve this problem, to prove the integrity of the whole architecture and prove the layer binding. So in ETSI, they provided 2 approaches. The first one is called single channel attestation. And in single channel attestation, as its name says, we have one channel between the verifier and the target, so the infrastructure. It is between the VM and the verifier. The VM is going to receive the challenge, the nonce, like it was called in the previous presentations. And the VM is going to request its attestation from the VTPM, its virtual root of trust. Once computed, it's going to transmit this attestation to the TPM, so that he can compute the attestation of the hypervisor. So it's like an attestation inside another attestation. It's a composite attestation. And the first one, the challenge is the challenge sent by the verifier. And in the second attestation, the challenge is the attestation of the VM. And then the composite attestation is sent to the verifier. So this approach enables surely to verify the integrity of VM and the hypervisor. It also ensures the layer binding between the two layers. But it has two main drawbacks. If we have 100 VM, or let's say even 5 VM, every attestation VM request will imply the TPM computations, because the attestation will go back down to the TPM. However, the TPM, as all of you know, is a very simple component, and he cannot, he's a resource constrained component. And the second drawback is that if we have multiple VMs, and the TPM is busy with the computation of the attestation for the blue VM, he will not be able to answer the request of the purple VM. Another also drawback is that the hypervisor is attested and reattested with every VM request, but it is the same hypervisor. So to solve these problems, at Etsy they proposed a second approach, which is called multi-channel approach. And in this approach, they propose to have two communication channels between the verifier and the target. The first channel is like the previous one, between the verifier and the VM. And in this channel, the VM will send its own attestation, only its attestation, using the VTPM to compute it. And the second channel is going to be between the hypervisor and the verifier, and it is going to enable the hypervisor to send its own attestation using the TPM computation. So this solution enables to verify the integrity of the VM and the integrity of the hypervisor. But unfortunately, the layer binding is it, because the two channels and the two attestations are computed completely in an independent way. But to gain two things in terms of efficiency and scalability. The VM uses VTPM, which are more efficient, and the computation is faster with the VTPM. So we have efficient VTPM attestation computations. And the hypervisor attestation is computed only one time, even if you have 100 VM. So here we thought that we can propose something to enhance this situation and to mitigate this problem, the layer binding and efficiency. So with Limoges, with the University of Limoges, we proposed a protocol where we opted for multi-channel option too. So we have two channels. We have the VM attestation over the first channel, and the hypervisor attestation over the second channel. The VM attestation is almost the same, but the innovation is inside the hypervisor attestation. So in the hypervisor attestation, we managed to add some linking information that will enable the verifier to make the linking between the VMs running on top of hypervisor and the hypervisor. Of course, as we opted for a multi-channel approach, we inherit the efficiency and scalability of this solution. Now, to give you more details about what did we really include in the attestation of the hypervisor and how did we include it, I need to go a little bit in depth and into a TPM attestation, as we use TPM here. So the TPM is a component that enables cryptographic computations. It has a couple of keys. The keys that interest us today, it's the endorsement key, which is the key that will enable identification and authentication of the TPM, and we have an attestation key that is going to be used in order to attest the host. And the TPM has access to some secure registers where the state of the system is going to be stored. So during the boot, every piece of code is going to measure the next piece of code and store the measures into the PCRs. When an attestation request arrives, the TPM is going to retrieve the PCRs and is going to sign this PCR with the attestation key, and this is the attestation. Now, how did we do to include the information linking, and what information linking did we add? Actually, we proposed a simple solution, but it's very tricky. We tried to manipulate the nonce, the channel that is inside the attestation. The intuition is actually to add the keys that are corresponding to the TPM that are associated to the VMs inside the challenge. So the hypervisor or the TPM of the hypervisor is not anymore signing only the nonce and the PCR, but it also signs the list of public keys of the VMs running on top of this hypervisor. Why is this possible? Because the VTPMs are running on the hypervisor. And if we trust the hypervisor, if the PCR are good, so we can trust the linking information that are available inside its code. So we get this. So we have a list here of the public keys of the VM that are running on the hypervisor. In the attestation of VM, we added here the key of the VM that is getting attested only for performance, let's say, so that the verification will be easier for the verifier. Then we proposed a security model. So it's the first security model for deep attestation protocol. We did not see security models for deep attestation before, but it's just a cryptographic model. It's not a formal proof with a proverb or an automated tool. So we used security games proofs and what we call redaction proofs. So we started with a basic property. We prove its security, and then we build on this property another one which is larger. Our first security is that we assume that a compromised state can be detected. This means that this is something that has been mentioned by Samuel, I think, about the reference values. We assume that we have good reference values, and if the received PCR, so the received state, is not good, we will be able to detect it because we trust the reference value that we have. Otherwise, like said Samuel, if the reference value is not good, so nothing is going to work. The second property is that we are able to identify and authenticate the components that are involved within the attestation. And this is thanks to the TPM and the VTPM and their signatures. The next property is the linking between the VM and the hypervisor, and this is through the addition that we did and the manipulation that we did with the nonce, with the challenge. And the last one, the last property is we made that only authorized entities are able to retrieve an attestation, because attestation includes sensitive information. It is including PCRs, and PCRs are the state of the system, the state of the component of the target. So if an attacker knows the configuration or the state of the hypervisor or the VM, he will maybe adapt his attack in function of this the known information. And this can be achieved by the use of TLS. Now, did we stop here? The answer is no. In our use case, we considered one verifier, but we said, why not considering multiple verifiers? And maybe here, some people are going to say, why did you so think about one verifier? Why didn't you start from the beginning using or considering multiple verifiers. Actually, both cases, multiple verifier and one verifier, are realistic in a mobile network context. The first one verifier, could be in the context where an operator is going to use an attestation framework in order to check the integrity and the state of his network. So it's one verifier and he knows everything about all the components in his network. And the second case, which I'm going to describe now, it could be in a context where the operator would like to offer an attestation server, an attestation service for verticals. So the verifiers could be some verticals who are using the network of the operator, and they would like to check that the VMs, the function, the network function that they are involved in these slices are in a good state. So we think, why don't using our first solution? Okay, it worked with one verifier, it could work with multiple verifiers. At the VM attestation, we have the code, we have the PCR signed with TPM and so on. Okay, that's good. But in the first use case, we have one authorized verifier. So we have either a verifier or not a verifier. But in this case, we have a lack of degradation. There are authorized verifier and non-authorized verifiers. So the VM has to answer only to its associated verifier, and not sending an attestation. The VM should play the dead when an unauthorized verifier tries to contact her. Why this? Because if, for example, the purple verifier is going to try to contact the blue VM, and the blue VM is going to answer and say, no, you are not my verifier, I will not answer you. The purple verifier is going to know that there is another VM which is rallying alongside my VM. So he will know the existence of someone else with his VMs over the network, over the infrastructure. And you would like not to share this information because a tenant or a vertical does not need to know who is running, who is his neighbor, or what is the number of his neighbors. This information does not we do not have to share it. And we discovered that actually playing the dead is something that could be achieved by TLS 1.3. So it's good news for us. And now if you go to the next part of the attestation, which is the hypervisor attestation, again, we thought that it will be, okay, let's use what we proposed previously by adding the public keys inside the attestation. The first issue that we had here, that at the first case, we have one verifier, one nonce. Here we have multiple verifiers, multiple nonce. The TPM is able to do one operation at one time. So when the TPM is busy by computing the attestation for the purple verifier, the orange verifier, the blue verifier are on standby. So it's not good in terms of performance. So we said, why not batching the challenges? So we will have one challenge, and so the TPM will have just one computation for all the verifiers. Okay, so we'll go back to the configuration of the first use case. One challenge, one code, one attestation. But remember that in the hypervisor attestation, we have two sensitive informations, the public keys and the PCRs of the hypervisor. And if we send the information like this, a verifier will know the number of his neighbors, the neighbors of VMs, and who is his neighbor. But he does not need this information. And maybe if he will know that he has a charging VM alongside with him, he will try to attack it in order to manipulate some charging for him. So this is an information that we do not want to share. And regarding the PTR, the verifier does not own the hypervisor. He just need to know that the hypervisor is in good state. He doesn't need to know the exact PTR, so the exact configuration and the exact state of the hypervisor. He just needs to know it's a valid state. And to solve this problem, we propose to use two cryptographic protocols, vector commitments, in order to hide the unnecessary public keys in the attestation. So when the blue verifier is going to receive the attestation, he will be able only to see his own keys, the keys of the blue VM, but not the keys of the purple VM or the yellow VM or whatever. And we also used the zero knowledge proofs in order to hide the configuration and the state, the PCR, of the hypervisor. So the hypervisor will prove that he is in a valid state without revealing his state. And it is by proving that he has a state that belongs to a public set of valid states. So to sum up, we proposed a privacy-preserving attestation in a multi-tenant environment, so with multiple verifier, with strong privacy properties. Our VM does not answer anyone. It answers only its associated verifier. Otherwise, it plays dead. The tenants does not store neither who is running alongside its VM, neither the number of neighbors, and the hypervisor does not reveal its configuration, its state. Maybe you are now saying we used, let's say, exotic or a little bit complex cryptographic building blocks, and that we may propose something which is less complex. Yes, but in one conditions or two conditions. Either we need to change and to modify the TPM, and when we started working on this problematic, we took the decision to not modify the TPM. We worked on a standard TPM. Either we consider a trusted third party, and also one of our conditions were not considering a trusted third party. That's why, so we used vector commitments, snarks, and so on. And as in the first solution, we proposed a security model based on mathematical assumptions. So what's next? We didn't stop working on deep attestation protocols, but this time we changed the context. We thought about attesting a group of nodes. This is what is known as collective attestation or swarm attestation. And it is a rich research area, but in the context of IoT. But in our case, we decided to investigate these protocols, but in an INFV and in a mobile network context. They have some similarities, yes, but there is also some deep differences between the two cases. We submitted this proposal at PETS conference 2024, so we cross fingers. We will have the feedbacks next week or the week later. And we also, we will try to look to other properties. So we look to the integrity at boot, maybe looking at runtime integrity, looking for key attestation. So there is other interesting properties that we started looking at. We will also look to other architecture, because the architecture that we propose to do, on which we proposed our protocols, it's not the standard one. There are others. There are architecture with multiple environment, execution environment. There are containers, there are functions, and so on. There are other root of trust. So we are starting thinking about enriching the architecture and trying to adapt our deep attestation protocols. So to end up, I think that Attestation is a really very nice tool, and it's enriching in any context, either in mobile network context or just in network context. And it is going to change completely the view of security. We're not anymore, we check the security one time and that's all, but with the Attestation, we are able to check the security in a continuous way, and it is something I think very interesting. And we can use it in many use cases. So I would like to invite you to take a look to the brilliant presentation and talks that we had last November in the Attestation workshop, where they presented use cases of Attestation on mobile network for certification or for routing. Here you can find the links for the scientific papers about the first and the second contribution, so with one verifier and multiple verifiers. The one that we submitted at PETS is not yet publicly available, but hope soon. And you have a proof of concept of the first Attestation protocol, so the ACNS paper, but it's just proof of concept. So to end, I would like to thank my collaborators, Thibaut Jacques and Christina Annette. Christina Annette is from the University of Limoges, and the work that I presented today have been funded by a European project, Inspire 5G, Plus, and a French project, MobiS 5. And that's all for me. Do you have questions?
Yeah, so now you can. Yeah, thank you very much. So, yeah, any questions from the audience?
What is it? Hi, Ghada. This is Hannes. Hope you can.
I had.
This is I was wondering, like, whether there's a possibility to change the terminology that Etsy uses on Attestation, because it always is sort of like rewires my brain when I'm on a IPF RAS sort of like train, and then I hear the Etsy terminology, which sort of like is totally different. That would be, I don't know if you can influence that. I'm not in Etsy, so I have no idea. But I think that would be good for the industry, so it's a bit more aligned.
I don't know if I can influence this, sincerely. But the issue with Etsy is that they don't have a specific or dedicated specification for Attestation. It's not like an IETF. There is a working group that has an RFC about Attestation, and that defines the architecture and so on. The Attestation in Etsy, it appears in different specifications. They have a report, I think. Yeah, they have a report which is dedicated for Attestation, but it's a little bit old. And Attestation appears in different spec. So I think to ask them to change their terminology, I don't know if I can do it. I may send a message, let's say, spread the message, ask them to consider changing, updating their terminology, but I'm not sure of the result. And I don't know if you remember that during the workshop, Yogesh from IRM proposed that we have a group of exchange from different organization, from different companies and so on about attestation. And there is BT who accepted to be part of this group of exchange. We still not have a group of exchange. We're just trying to set up this group. But as Les from BT, who presented during the workshop, he is the chairman of HCNFV6. So maybe if the group of exchange will be born someday and Les join this group, maybe we can have some influence on HC terminology, I hope.
Point to be Thomas to present the RAS terminology.
Sorry, Alice, I wrote the original terminology in 2015. But before that.
So that's an excuse.
That's my fault.
That's an okay excuse.
Maybe have been the other way around, like the rats should have followed because one of the agenda items that it will collaborate with all other existing standards, and that's one of my long-standing complaints with.
You're asking IETF to collaborate with ETSI, and that's not like IETF very well.
Okay, so Ghada, I have one question from my side. So at a couple of points you were mentioning the TLS protocol, and I was kind of wondering if the remote attestation which is signed, at what point of time is that evidence signed? Is it that the proposal contains the evidence signing after the TLS handshake has completed, or is it the other way around?
Sorry, but I didn't hear you very good. Can you repeat, please?
Yeah, sure. So what I'm saying is basically I'm at a couple of points. I think it's slide I have in my notes. So it was 10 or something like that. At a couple of points.
Slide 10?
Yes. I think so. I need to check my notes. So not this one. So let me see. I have. No, I think I don't have the slide number. So if you scroll really up and down, so you have in a couple of slides.
The previous one? Previous one?
So here you can TLS, not this one. So not this. Okay. Anyway, so what I was interested in understanding was whether so now there are two things, right? So there is as Carson was also presenting now, you have remote attestation protocol and the TLS protocol, right?
We have, you are talking about this one, I think, when I mentioned TLS, that's it?
Yes, yeah, exactly this slide, yeah. So this is one of the slides where you were mentioning like the only authorized parties can receive the attestation. So now I'm kind of thinking about the properties that we verify and even the implementation that's there. So is it taking into account what is the kind of the relation between the two? That's probably my question. So one way of doing it, because there are at least two ways of doing it. One is that you do the signatures before the TLS protocol starts, and more precisely the handshake protocol within TLS. And the other way is that you have established the TLS protocol, like the TLS session, like the handshake protocol has now finished. And afterwards, you do that signatures, and then you submit that in the RADS terminology, like the evidence, in this case, your code. So is it that the code is transmitted over when the TLS handshake protocol has completed, or is it the former one?
Actually, here, for example, I mentioned the use of TLS, but in the first case, we can use just a simple key exchange protocol. We do not, because TLS is a very huge protocol. We can just use a key exchange. So suppose we use TLS. TLS, actually, we use the basic TLS just to secure the communication between the two entities. But of course, if we think about what has been previously presented, by combining TLS in that station. Actually, I don't know if we will need our protocol, or we can combine it with TLS, because it's not just an attestation, it's deep attestation. So I don't know.
Okay,
But
so what you said, or maybe your verification better. So you, in the verification, you don't have TLS, you assume that it is correctly established and that's it. So you don't have any, let's say, kind of a verification of the TLS protocol itself, right?
yeah, there is no communication between the attestation and TLS. And what we propose with TLS is just used to secure the communication, and then over TLS we build an attestation protocol that I described. But I think that it is something that we should also think about it, if we can combine our protocol to the TLS, and how. Maybe you can get inspired by the work that is already done by the colleague who presented today.
I will use that tomorrow, so some of our work related to that, but it's on the symbolic level, and I assume when you go to the computational, there will be huge kind of issues with that. But anyway, that's let's thank the speaker again. Thank you very much, Ghada.
Thank you.